Good morning. Thanks. A little audience participation first thing. All right, so we have to march along. Intense summer course, everything crammed into a short period of time. So here we are in a new chapter. Fundamentals of spectral photometry. There's going to be a little bit of material from chapter 18 sort of drawn into this, but by and large, this is like all chapter 17 stuff. Remember at the beginning of class, we talked about how, well, we talked in general terms. What are analyses in general? Then what are chemical analyses? You know, they're operations that you would carry out to get some information about a chemical system that's under study. And there's three kind of major kinds of analyses that are based on the kind of information that you get from the chemical system. You know, there's qualitative analyses, quantitative analyses, and what was the other one? Structural analyses. This course focuses on quantitative analyses, yes. And so then we went on to define or classify quantitative chemical analyses into their nature. You know, the nature of the kind of information that really is at the heart of it. And then we classified chemical analyses into volumetric. What were the other ones? Gravimetric. Yeah, we're going to talk about that on Monday. Electrochemical. And spectroscopic. Or spectrochemical. There's different words. They all kind of mean the same thing. So here we are. We're going to talk about the fundamentals of spectrophotometry. But really what we want to get ourselves able to do is kind of understand some of these spectroscopic analyses that are designed to quantify. Okay. To understand this kind of analyses, you know, it's really good to have a good understanding of light. You know, the physics of light is really, really complicated if you really get into it in a big way. But without having to get too drawn into Maxwell's equations or quantum mechanics, it's relatively straightforward to understand some important aspects of light. And we're just going to cover the basic things about light and hopefully not go into any excess detail that we don't need to. But to really be a good student of analytical chemistry and to have a good grasp of this stuff, you should know a little bit about the basic wave properties of light and the particle aspect of light. As it turns out, there has been a big kind of debate all throughout history as to whether light was made up of particles or waves. And sometimes some new evidence came out of somebody's experiments and said, you know, light is a particle. That's it. End of story. That's all she wrote. But then someone would do some more experiments and say, no, light is made up of waves. It must be waves. Oh, okay, well, forget about the particle theory. Forget about the particle theory. Focus on waves. But then as it turned out, they both can't, they can't be ignored. Both of them have to be sort of taken together. And electromagnetic radiation, it's neither a particle or a wave. It's something more physically fundamental than that, that could be a particle or a wave, depending on what kind of experiment you do to it. So, but we're not going to go into sort of the quantum mechanics of light at all. The things that cause it to be a wave or a particle, depending on how you look at it. We'll just focus on the key things that we need to know, these two descriptions. Okay. But whether you look at it a wave or particle, you end up looking at light as a phenomenon involving energy. You know, all waves, and you're probably very familiar with a few different kinds. I'm sure you've been at the ocean and seen water waves travel across the ocean. I'm sure many of you probably play musical instruments. Maybe there's somebody in here who can play a pretty mean freebird on the guitar. Who knows? There's sound waves, like maybe the waves I'm emitting right now. All waves, anyway, regardless of whatever kind of wave they are, involve the motion of energy. And light is no different. Electromagnetic radiation can really kind of nicely be understood based on the way energy is involved. So without going into that too much, and I'm tempted to because I'm interested in it, we'll just go on to the key stuff here. Won't get us off track. Okay, so if we think about waves, you know the idea of waves. You probably studied them in science a few times. The waves involve some medium. There has to be a medium. Like say if we were talking about a water wave, it's the ocean. And so we talk about that wave, or we look at that wave in terms of what is happening to the height of the ocean at the surface. And so if there's a wave, that medium is jiggling, going up and down. And so it takes energy to distort the wave. It takes energy to distort the medium. It takes energy to lift this part up. It takes energy to force this part down. There's energy in the ocean when this is happening. But you know the waves move. So energy moves from, say, the source of it to wherever it's going to land. So in sound waves, maybe it's the pressure of the air, like the density of the air, that's going up and down when a sound wave passes through the air. But anyway, regardless of the kind of wave, there's always something that goes up and down, up and down, up and down. And with a light wave, it's no different. But with a light wave, there's actually two things that go up and down. There's an electric field that goes up and down, and there's a magnetic field that goes up and down as well. And they're actually at right angles to one another. Fancy physics word would be orthogonal, that they're completely different. They're right angles to one another. They oscillate independently. Okay. So electromagnetic waves, and I'm going to switch back and forth between electromagnetic radiation and light. Really, as a scientist, I should be maybe more careful when I use the two words, but the two words get used interchangeably. But we will point out the difference between electromagnetic radiation and light. So anyway, that wave unfolds in time. So say you've got a light wave that's being emitted by the light up here. Okay. Well, that wave sort of unfolds in space and time. And so there's two ways of looking at waves. If we could somehow look at the wave and freeze time. So this is like taking a snapshot. Time is frozen. See, the variable on this axis is distance. Time is frozen. So if we were to do this, freeze time, but take a snapshot of it across distance, we would see this, the fact that it goes up and down, up and down. And we're going to focus on the electric field from now on. This goes up and down. And so when we think about what this thing is doing in distance, we can identify this thing called a wave length. Okay. And we know that it's going up and down and back up and then over and over. It's going through these cycles. So the wavelength we define as the amount of space that it covers, that it moves through as it does one cycle. Okay, so the key thing is this cycle. As it does one cycle, it moves through space. The wavelength is the amount of space that it covers during that cycle. Okay. But, that light wave, like all waves, is kind of unfolding in space and time. And so if we focused on one point in space and just looked at what the wave was doing as time went by, then you would get this kind of picture. Looks a lot the same, but the axis is time. And so back to the idea that this wave is doing these cycles, and really it's just repeating itself. It's like repeating itself over and over. It's doing the same thing over and over again. You know, when I was a kid, I used to have a really bad problem with stuttering. Really bad. And it used to get worse if anybody bugged me about it. And so sometimes the kids would say, "Hey, what's your name?" And I would just fall into it. I'd say, "Dave." "Dave, ha, ha, ha." And I go, "Dave, Dave, 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 Dave." But anyway, just repeating myself. That's what the light wave is doing. It's repeating itself. It's doing the same darn thing over and over and over again. So if you understand one cycle, you understand them all. You just put them one after the other. It's like a car going down the road. It's just the rotation of the wheels just over and over and over again. Okay, so if you freeze it in space and you look at it in time, then you can see this parameter called the period, which is the amount of time that it takes for the wave to repeat itself. Just like if you looked at it in space, the amount of space that it takes for the wave to repeat itself is called what? Wavelength, yeah. If you look at free space and look at it in time, the amount of time that it takes to repeat itself is called the period. And the period is connected to this frequency, which we'll discuss in a minute. Okay, so we're talking about the wave aspect of light. And so waves can vary in their wavelength. There's a whole range of different kind of electromagnetic waves, and they vary in wavelength. Some waves have really short wavelengths. You see here, this is like a double axis. We'll talk about the frequency axis in a minute, but let's look at this wavelength axis. All possible waves are can be described on a line like this, a line of wavelength, excuse me. And so down here you have waves that have really short wavelengths. So you move this way, you go through waves that have longer wavelengths. Over on this end, at this extreme, you've got the waves with really long wavelengths. Now, fundamentally, they all are kind of the same. They are electromagnetic waves that carry energy through space. But what the waves are possible or are capable of doing really depends upon wavelength. So even though they're kind of all the same, they have very different effects when they interact with matter and things. So anyway, all these waves have different wavelengths. But however, although they have different wavelengths, they all travel at the same speed. So even a wave that has a really short wavelength travels through space at the same speed as a wave that has really long wavelength. Okay? And so the wave goes through cycles and moves through space with some repeated cycles, and it covers a distance lambda, or the wavelength, each cycle. So that's not unlike a person moving through space by walking, doing these cycles of moving their legs, right? But each time they go through a cycle, they cover some characteristic distance, which you might call the stride. Okay? So I guess if there's no restriction on my velocity, like I'm not a light wave at this point, I'm not bound to any particular speed. You can see there's two things that control how fast I move, right? There's my stride. If I step at the same frequency but make my stride longer, I will go faster. Or if I do both, increase my stride and my frequency, you can see then I move faster. So these two things, wavelength, the stride, and the frequency, control the speed. But now I'm going to become a photon. I need someone else. I need some help. I need someone else to be a photon. Drew, can you help me with this? Okay, so Drew and I are, Mr. Daly and I are going to be photons. Okay, because we're photons, we have to go at the same speed. Okay, so we're going to go, it's a little narrow, but we can do this. Okay, we're going to go at the same speed, but we can't have the same wavelength. You want to be the short wavelength or the long wavelength photon?
I'll be long wavelength.
Students always pick that. Okay, so I'm the short wavelength photon. We're going to cross the room at the same speed. Okay, right. So you're just going to stride, just walk normally, and I'm going to keep up with you. Okay. Okay, go a little faster. Okay, thank you, thank you. You get the point? You get the point? The wave with the short wavelength, which unfortunately was me, has to have a high frequency to compensate, so they go at the same speed. So therein lies the relationship between frequency and wavelength. They are inversely proportional to one another. And therefore, students of chemistry can never escape questions like this one. Okay, looks like everyone's in today. All right, so how do you solve this one? Which you learned how to do before. What you're asked to find? Wavelength. How do you rearrange this equation to get something for wavelength? C, the wave speed of light over the frequency? Yes. Okay, so you have been learning about electromagnetic radiation. Let's just make sure my sound is not muted. Then we had one time before we had a problem with volume, but let's see. problem. Okay, well, unfortunately, technology people have not helped me out here. Okay, so basically, I'll give a voiceover, okay? So we now know that there's a whole range of possibilities of electromagnetic radiation in terms of wavelength, a really great range. They can go from having very short wavelengths to very long wavelengths. Or if you want to talk about in terms of frequency, they can go from having very high frequencies to very low frequencies. And so if you consider the whole range of electromagnetic radiation, it's kind of like a line. And in fact, it's a very long line. So in this video, they're saying, think of this line as being like a roll of movie film that you stretch out. And it stretches, the entire electromagnetic spectrum stretches all the way from it's like some town in Alaska on the coast, all the way down to some small town in California. It's very long, very long. But the amount of radiation that we can see with our eyes, the visible range, the visible portion of the whole electromagnetic spectrum is very small. It's like, they say, one frame in that whole distance from Alaska to California corresponds to the amount of radiation that we can see with our eyes. So there's a whole lot of radiation that we can't see with our eyes. A lot of longer wavelength and shorter wavelength radiation. I'll have to post this on YouTube if anybody cares to look at that. But if you look at this line, this representation is actually a little bit deceptive. It makes you think, well, the visible range is a pretty substantial little chunk of all the types of radiation. But in reality, this is a logarithmic scale. You know, one step here is 10 to the 6th to 10 to the 7th. And the next step is 10 to the 7th, 10 to the 8th. It's kind of like the pH scale. One change in pH unit corresponds to a factor of 10 changes in hydrogen ion concentration. So people have to do this, build this into like a logarithmic axis to make it something that we can use, we can present in class. But if you stretch it out in reality to how long it would be if it was not a logarithmic axis, then you could play these games and say, well, that corresponds to a distance from someplace in Alaska to California. And the visible spectrum is like, 2 or 3 centimeters in that whole line. So in reality, this is a really, really small bit of the electromagnetic spectrum. Okay, so that's a quick review of the wave aspect of electromagnetic radiation. But it's also really good to know something about the particle aspect of light, particle description. And the main idea here within the particle aspect is that these little particles of light each carry a little bit of energy. We know that the overall wave, light wave, carries energy. You know that. You've gotten into your car on a hot summer day. And, it might be 95 outside, but you get in your car, and what's the temperature inside your car? It's about 140. You burn your butt, right? Because there's energy in that light that's landing on your car, and that energy in light is being turned into heat energy, right? So we know that light waves carry energy, like all other kinds of waves, but according to this theory, light is composed of a whole bunch of little particles, and each of the little particles carries a little bit of energy. And so Max Planck figured out a way of calculating the amount of energy carried by each particle of light, which he called photon. And he figured out that there was a direct relationship, a direct proportionality between the energy of the photon and the frequency. There's a direct proportionality. And he did some experiments. When he first discovered this, he was doing some experiments studying the way things glow when they're heated up. And he estimated what this constant must be. You know, this factor of proportionality between energy and frequency. So he was the very first person to estimate what the value of this constant of proportionality is. And this was a big breakthrough. And the particle theory of light was adopted widely, explained a lot of things. A few years after Planck announced that he figured this out, Einstein used the particle theory of light to explain the photoelectric effect. And then it really became solid, really strongly, widely used in science. But anyway, other people came along and did more careful measurements to estimate the value of this constant. But even though other people have contributed to finding, you know, a value for this constant, which is a lot of decimal places, it's still called Planck's constant to give credit to Max Planck for his initial sort of flash of insight that light was actually made of particles. Okay, so let's see. I can ask this kind of question. All right, so we have two equations. We just saw this equation. And we talked about how the energy of a photon of light is directly proportional to frequency. It's actually frequency multiplied by a constant. But we previously were talking about this equation. And so frequency equals the speed of light divided by the wavelength. So we can just do this substitution and look at this equation two ways. So we could say directly proportional to frequency, but inversely proportional to wavelength. So these are the sort of fundamental basic relationships that we want people to sort of have a good understanding of. So, okay, you've got everything you need. You've got Planck's constant, you've got the speed of light, you've got everything you could possibly need. Let's try this question. All right, great. No need to spend any more time on that. You know how to do things like this. It's good. Can you do this? Oh, maybe Avogadro's number would be useful. Pardon? Okay. Okay, so this question is asking about the amount of energy carried by a certain number of photons. You know, we learned how to calculate the energy for single photons, for, you know, the little units, like one of them, each little entity carries amount of energy that we can calculate by this. So let's go through this as a first step. Calculate the amount of energy carried by one photon. Then we'll go to the next step. So the energy carried by a photon, we can calculate its Planck's constant times the speed of light divided by the wavelength. So Planck's constant, 6.626 times 10 to the negative 34. Now, Planck's constant has got some interesting units. Joules times seconds. Okay. But we're going to multiply that by the speed of light, 2.998 times 10 to the 8 meters per second. And then we're going to divide by the wavelength, which is what? 527 times 10 to the negative 9 meters. Can I do that? Got to turn nanometers into meters. Okay, so we're calculating the amount of energy in one photon. See what the units are doing. So meters on top cancels meters on the bottom. Seconds here cancels seconds here. And so we end up with some number in units of joules. How many joules did we calculate for this first part? Sorry. 3.769 times 10 to the negative 19th joules. So this is the amount of energy that's carried by one of those photons. Does anybody know how much energy 1 joule is? Do you have any idea of feeling for how big a joule is? If you had a chocolate bar, you went to the store, you bought a chocolate bar, your average chocolate bar, not some dinky thing, but your average sort of big Milky Way chocolate bar, something like that. And you held it in your hand, but you raised it by a meter, okay? That takes some energy, right? To lift things up to higher potential energy takes energy. To raise that chocolate bar by 1 meter, that's approximately 1 joule. It takes 1 joule of energy to raise a chocolate bar by 1 meter in the Earth's gravitational field. So this says each photon only carries 4 times 10 to the negative 19 joules. Think about how many of those photons you would need to raise that chocolate bar by a meter. Each photon only carries a little wee tiny amount of energy. They're tiny, just kind of like atoms are tiny. Joules, well, let's do this. Per photon. But this question asked us not about the energy of single photons, but of mole of photons, right? So 6.022 times 10 to the 23rd photons per mole. So we just multiply by Avogadro's number. But what's the other trick? 6.022 times 10 to the 23rd photons per mole.
Oh, okay.
Yeah. Because we're going to get something like an amount of energy per mole. Okay. But this is in joules. We want the answer to be in kilojoules. So what other conversion do we need to do? 1 kilojoule on top for how many joules? For 1,000 joules. D. D serves me correctly. It is D. Okay. All right. I like those kind of questions. Okay. So why do we have to learn about both descriptions of light? Why do we have to worry about waves and particles? Aren't they two separate things? Well, as it turns out, in a lot of experiments, when light moves through space, and you don't stop it, you just let it keep going, but maybe you do something to direct where it goes, but you don't stop it, it behaves like a wave. Behaves like a wave. You might think of diffraction effects or something like that. That's when it's moving. You're maybe directing it a little bit, but you're not stopping it. It's like a wave then. But as soon as you stop it and make those photons hit other things, then that's when it behaves like this particle, and this calculation of the amount of energy becomes important. And trying to understand what happens when that photon of light hits an atom or molecule or whatever kind of particle it's hitting. Okay? And so now we're going to move on and talk about the phenomenon that can occur when light basically hits atoms or molecules. Okay, so now we're going to move on from our basic understanding of radiation that we've been sort of developing by review here to going on to understanding, okay, now how do we talk about how electromagnetic waves or photons, however you want to think about them, interacts with matter. Okay, so a bunch of different phenomena can happen when radiation interacts with matter, a whole bunch of different things can happen. Here's like just a partial list of all the things that can happen. But our focus is going to be on the things that happen when radiation is absorbed by matter, absorbed by the molecule or atom or whatever it interacts with. But then there's a few phenomena, a couple of phenomena we're going to talk about that are sort of can be seen as subsequent to that. After an atom or molecule absorbs a photon of light, then other processes can happen. Specifically, we're going to talk about fluorescence and phosphorescence, two separate things. But they can both be sort of triggered or caused by the absorption of light. Okay. So these little molecules can impact the atoms or molecules that they are absorbed by. And the impact, the way that the impact that the photon has depends upon the wavelength of the photon. And specifically, you could say it really depends upon the amount of energy that the photon carries, right? Energy is directly proportional to which wave parameter? Energy is directly proportional to frequency. Yes, yes. Okay. So here, we're going to higher and higher frequencies. So we're kind of like thinking about, okay, what happens when light is absorbed as a function of the frequency of the photons. So down here, these are high energy carrying photons. These are low energy carrying photons. And so this is a list of the effects. So let's start down here at low. Somebody has an electric organ, church organ, with like a low note. So this is low energy of photon. A low energy photon, say like in the microwave region, can cause a molecule to rotate faster. Actually, as it turns out, it only takes a little bit of energy to cause a molecule to rotate faster because those rotational levels are closely spaced. Okay, but molecules can do a bunch of different things. Molecules can vibrate as well. Molecules, like say two atoms, you've got some really simple diatomic molecule. So it can rotate with those atoms going round and round like that, or it can vibrate. And as it turns out, the energy differences between the vibrational levels is greater than the rotational levels. It takes an infrared photon, a little higher. Somebody play a little higher note on the organ. Okay. Now you go even farther. You go down into the visible and ultraviolet region. Okay. Those photons, in relation, carry even more energy. Those photons that carry more energy, they're able to move electrons around. So far we're just talking about making the nuclei move, either some rotation or some vibration. But now these photons have enough energy to move electrons around, to lift electrons from one orbital to another one. And so in the visible region and in the ultraviolet region, you can lift electrons. And this depiction sort of shows a wave state that looks like this, being promoted to a wave state that looks like this, from a bonding molecular orbital to an anti-bonding molecular orbital. But anyway, visible and ultraviolet. But it's a fine line. If you go farther down in energy, not only are those, if you go to higher energy, I should say, not only are those photons capable of moving electrons around, they've kind of reached a point where they're able to actually move an electron so far that the molecule breaks. And so if you go to high enough energy, then you can say, here's the effects. The photons can break bonds and ionize molecules. So what do we mean by ionize? What does that mean, ionize a molecule? Take an electron right off of it So in the UV vis, you can like lift an electron with the photon, but if the photon has even higher energy, not only can it lift it, it can like knock it right off. So ionization is just kind of like the next thing that can happen at higher photon energies. So anyway, this is one of your homework questions. What are all the effects that photons can have? So we're going to start talking about absorption. And so this is sort of a depiction. Try not to be overwhelmed by all the information on here. Let's focus on this first box A. Absorption, as you've learned a little bit now that you had to do yesterday's lab and pre-lab, involves radiation. And our trigger for being aware that absorption is happening comes from measuring, keeping track of the intensity of the radiation and that is hitting the sample. And if the intensity of the radiation after the radiation has gone through the sample is lower, say P, after it's gone through the sample or been transmitted by the sample, if that intensity is P, and P is less than the intensity was when it was going in, we'd say, oh, look, the intensity has become lower than what it was when it went in. Another way for that, another way to say that is absorption. Oh, well then let's call that absorption because some of that radiation was absorbed somehow. It went away. And you've all heard about the conservation of energy. Energy is neither created or destroyed. So if the light beam carries a certain amount of energy, and that energy in the light beam decreases, well, energy neither created nor destroyed, that energy had to go somewhere. So that energy now belongs to the sample. Just like your car got really hot when it was sitting in the sun, because the energy that was in the light, the radiation coming from the sun, got turned over to your car. Same thing here. When the absorption happens, energy gets deposited here. We're going to talk about all the things that happen to the energy. Okay, but so this is like an energy level diagram. As we discussed, when there's absorption, that sample of matter must have some way of storing the energy that's been given to it. And so it's not specified whether these are rotational levels or vibrational levels or electronic levels, but if there's absorption of light, those atoms or molecules must be going through some energy levels, being lifted from one energy state to another. And so within this system that has two energy levels, I guess it's possible to go from the ground state to either the first or second excited state. So within this system that has three levels, there's two absorption transitions that are possible, okay, at two different energies. Which is greater, energy of this transition 1 or the energy of this transition 2? E2, yes. Though it's not explicitly said there, maybe it got cut off. That is an energy axis. 0 is usually what we call ground states, and then level 1, and then level 2. So if we start off with all the molecules or atoms in their ground state, they can either absorb here or here. And so this is an axis, an energy axis. And so the length of the arrow corresponds to how much energy it got lifted up by. Okay, so E2, energy of that second transition is greater than energy 1. Okay, so now thinking about the relationship between energy and frequency, there's light waves involved here. These are two different photons that would have different energies that would drive these two absorptions. Which photon would have the shorter wavelength? The photon that created transition 1 or the photon that created transition 2? Which photon would have the shorter wavelength? 2. Yeah. Why do you say that? Yes. Yes. And it needs to have more energy. Okay. So this here in panel C, this is kind of what the absorption spectrum might look like for if we did the absorption experiment on this system. You know, as we'll discuss in a few minutes, we would have to scan this system, measure absorbance at a bunch of different wavelengths. And as we scanned across here, we would find that, oh, it absorbs light. You know, let's start down here. At lambda 2. Not down here, but once you get to lambda 2, it does absorb radiation. So the absorbance goes up, then comes back down. Down through here, there's no absorbance. But again, once you get down towards lambda 1, where that photon just perfectly matches the energy that's needed for the transition, photons get absorbed again. And so the absorption spectrum is closely tied to the transitions between those energy levels. Okay. So down here is just a rough schematic diagram of what an absorption spectrometer looks like. We do things like record absorbance spectra using absorption. We have to use a tool, an instrument, a machine that you've already been playing with. You know a little bit about the spectrometers. And this is a rough outline of the schematics. Okay. An absorption spectrometer has to have a light source. It's got to have something that gives off the light that's going to be absorbed by the sample. But most lights in this room, lights in the headlights of your car, lights in your homes, apartments, or whatever, give off a whole range of radiation. But when we do these measurements, we don't necessarily want a whole bunch of different photon energies going through the sample. We want to control it. We want to be able to scan. We want to do a measurement at lambda 1, there, and then there, and then there, and then lambda 2. So we want to be able to control which wavelength goes through the sample. This thing puts off a whole bunch, but we don't want to let them all through. We only want to let through narrow wavelength range at one time. And so we need this thing called a monochromator. I've got a better picture that kind of shows this in a second. But anyway, then after the monochromator, then there's the sample. You've got your piece of your matter in there. You know, you put in your cuvette if it's a solution. Just put in there. And then there's the detector that measures the intensity of the light. Okay, so that's absorbance. But absorbance is something that you can quantify. And so with absorbance, we start with these intensities of the radiation kind of after the sample and before the sample. Or you can say the intensity of the radiation that goes through the sample compared to the intensity of the radiation that does not go through the sample. And so anyway, you can compare those two. The detector measures these things, P and P naught. And then you can take the ratio of those, which is called the transmittance. So the transmittance is like, it's a fraction. It's somewhere between 0 and 1, right? What would the value of this fraction be if all the light that hit the sample actually went through it? So P was equal to P naught. What fraction would that be equal to? 1. Yes. Okay. But like fractions, like all other kind of fractions you're used to working with, fractions are nicely, in a lot of cases, shown as percentages. So this fraction transmittance is often reported as percent transmittance. But basically, to get the percent, you always do the same old thing. You multiply by 100. Okay. But then, from the intensities, from the transmittance, another thing is calculated, the absorbance. Absorbance is not the same as transmittance, but it's calculated from transmittance. So absorbance, you could write it in a few different ways, but it's all just like mathematical rearrangement. P naught over P, or you could say absorbance equals negative log. If I move the negative sign out here in front, what do I have to do to this ratio? Yeah, P over P naught. But P over P naught is T. So I could write this as absorbance equals negative log of transmittance. And so just a quick slide talking about, in reality, this picture showing like P naught being before the sample and P being after the sample is a little bit misleading. In reality, P and P naught are measured in a way that's better described here. And this is more like a schematic diagram of the spectrometer that you used in your laboratory. Because we measure P naught as the intensity of the radiation after it's gone through a cuvette that contains everything except the sample. So something that contains everything, the same solution, maybe other things that might be there, present there, ions or whatever, everything except the sample, we'll call a solvent blank. But then, in nice instruments, we simultaneously put into the instrument both the solvent blank and the sample. And then you have a detector that's measuring the intensity of the radiation. The intensity of the radiation after it's gone through the whole shooting match, including the sample, then is P. And so this is referred to as a double beam spectrometer. There's two beams of radiation. One that goes through the reference cell, which has the blank. The other beam goes through the sample cell. Okay. And in that Shimadzu, there's different manufacturers of spectrometers, but that Shimadzu that you used in the laboratory, didn't you have to do that? You had to simultaneously put in the blank and your sample at the same time. There was like the front. You had to know the difference between the front and the back. Where did the reference go? I guess the blank, the back. Yeah. So to use these things properly, you need to be aware of which goes where. But you put them both in at the same time in the double beam spectrophotometer. And I expect that some people from this group are going to take instrumental analysis with me. So this is almost just like a little trailer, a little prelude of some of the things we're going to talk about in instrumental analysis, if you have to go there. But anyway, so this is how P and P naught are actually measured. But that's a critical start. You have to get good measurements for P and P naught. Okay. So we'll have some clicker questions, a sort of little small barrage of clicker questions. It's a numerical. Got some stuff to cover. Some serious stuff to cover. Got some stuff to cover on Monday, too. So absorbance is equal to negative log of T. So if P is equal to P naught, then what is T? 1. Of course, then if you express that as a percentage, it'd be 100%. So log of 1 is what? 0, yeah. Then, okay, you take 0 and multiply it by a negative sign, okay? So it's actually negative 0. So let's see how many people put in that.
Negative 0? Dang, I get that.
All right, well, second best. You know, I'm totally joking. I'm pulling your legs. You guys are a little bit sluggish. Got to get some excitement going in here. Okay, another question. Very similar. Okay, everyone in? Yay. So let's see what we got. Well, 1% transmittance corresponds to what value of T? 0.01, yeah. Take the log of that. What's a log of 0.01? Negative 2. But then you multiply that by a negative sign. Then it's 2. Yay. Yay. Don't forget how to do things like this on Friday. Okay? All right? Yeah, have you seen the slides? There's about 25 of these.
That's what, yeah. Like,
Yeah.
my question is really important.
That's what employers and graduate schools need. They need people who can do that. Yes.
They do. Transmitters.
Yeah. And you're learning it well.
Hey, we go fly out here. We're at that.
Pardon? Okay, we'll just do one more. You know, the other ones were kind of repetitive. They're all the same. But this one is slightly different. Now you're given before you were told transmittance and asked to calculate absorbance. Now it's the other way around. You're told absorbance. Can you calculate transmittance? Okay. All right. So switching back and forth between absorbance and transmittance, mathematically, it's a lot like switching between pH and hydrogen ion concentration, right? It's kind of like the same. So how do we, what do we have to do with this equation to solve for transmittance? Yeah. Okay. So we don't need to do this one. Okay. Yeah. You're going to like the other ones we do too. Okay. So the next thing we're going to talk about is the Beer-Lambert law. No, actually, let's use the nice power of the iClicker system. I'm going to do something right now that I could never do with the CPS. Okay. I'm going to invent an absorbance spectrum. Okay. Say, absorbance spectrum has what on the y-axis? Absorbance. Yeah, you have some sample. You have some sample that you're passing light through. And you get P over P naught. You calculate absorbance. And that's what you're putting on the y-axis in an absorbance spectrum. And so what's on the horizontal axis? No. Wavelength. I'm getting a little bit ahead of myself. Let's go there. Okay, let's just leave that up there. Okay. You guys maybe are thinking about a Beer's law plot, absorbance versus concentration. But I just want to go over an absorbance spectrum just a little bit more real fast. Okay. An absorbance spectrum plots absorbance as a function of wavelength. Okay. So let's think about your lab yesterday. Okay. So let's say you took one of your standards containing a known concentration of caffeine. And it gave an absorbance spectrum that looked like this. Caffeine is a molecule that it'll absorb a bit of a range of wavelengths, but we can find that wavelength where caffeine absorbs most strongly. At what wavelength did caffeine absorb most strongly? Around 274. Okay. So let's imagine you took your solution, your unknown that had maybe 4 milligrams of caffeine per liter. Okay. You put it in the machine. And you got an absorbance measurement, say, of 0.3 exactly. What is the percent transmittance? Okay, that's the question. It's going to be the question. It's a numerical type question. Where's my? All right. So how did you, before we look at the answers, I'll ask you, how did you answer this? The same way, right? You know, last night, you know, I was looking at YouTube. And I like learning from videos, and sometimes if I find really good videos, I'll use them in class. So I was on YouTube last night, and I was looking at this video where someone was talking about absorbance and this type of stuff. And the instructor said, if the absorbance is 0.3, that means that 70% of the light is transmitted. It's like, what? Pardon? Did I hear that correctly? Skip back. If the absorbance is 0.3, that means 70% of the light is transmitted. So, you know, obviously, it's not quite so simple. You can't say, oh, this much is absorbed, therefore this much is transmitted. It's, you know, that's a common mistake for people to make. Even people who are probably getting paid by someone to make YouTube videos, because it looked like a somewhat professional YouTube video. But it was such a big mistake. I was like, hello? I had to comment on that. Okay, so okay. So the Beer-Lambert law. So now that we know about this parameter called the absorbance and where that comes from and how absorbance is related to transmittance, the next thing that we're going to learn is the way that absorbance depends upon concentration. So actually, as described nicely by the Beer-Lambert law, the amount of absorbance depends upon three factors. You know, you've got some sample cell with your sample in it, light passing through it. The absorbance depends upon three things. Molar absorptivity. And molar absorptivity is just a property of the molecule. Some molecules might absorb light very strongly. Like, say, the molecules in your shirt that's very darkly colored. Molecules that absorb light very strongly have high values of this molar absorptivity. Okay, so it's a constant which depends upon the molecule in the sample. B, what is B? Path length, yes. C, okay, so obviously, if you make the path length longer and longer and longer, the absorbance gets higher and higher and higher. And so C is the concentration. So absorbance depends upon these three things. But so if we want to focus on the relationship between absorbance and concentration, we have to keep these things constant. Well, as it turns out, epsilon, the molar absorptivity, is a constant. It just depends upon the molecule you're using. And then to keep B constant, we always do our measurements in the same size of cell. Anybody remember what the standard path length is? 1 centimeter, yes. Molar absorptivity. And maybe, you know, it's a nice way, I think it's a nice way, that you can understand kind of what molar absorptivity is. So Beer's law is always true. Okay, it's always true. So what if we set concentration of whatever analyte we're working with is 1 mole per liter, okay? And we set B is equal to 1 centimeter. Then absorbance is equal to the molar absorptivity if the concentration is 1 mole per liter. So that's, I guess, why it's called the molar absorptivity. It's how much the sample would absorb if the concentration was 1 mole per liter. You must not have been looking because it was there. Okay. You must not have been.
You turned on the clicker question by accident.
I want to know if you know
Yeah. Okay. Okay. So you would have filled this out. But the audio's not working. Hey, you guys, fix the audio. Keel, I know you're watching. Fix the audio in here. Pull out your wallet. Okay. The audio does not work. Okay. So I'll post that video as well on the George View, if anybody's curious about it. Okay. One of the homework questions is going to ask you about, in practice, when Beer's law doesn't always work that well. So, in principle, the equation Beer's law is always true, But you can have difficulty making the measurements under certain situations. The problem is, the problems with Beer's law can really be understood if you think about the way the measurements are being made. And say if you have a double beam spectrophotometer, you have radiation simultaneously going through the blank and the sample, and then they go to the same detector. Well, there's usually some little device in here that's called a chopper that kind of decides which way the light goes. So it kind of alternates. First light goes through the blank, and then a millisecond later, light goes through the sample. So it doesn't really measure them both at the same time. It may seem like that, but really on a short time scale, it measures blank, then it measures sample, then it measures blank, then it measures sample, with the assistance of some fancy electronics. So anyway, Beer's law is based on intensities. P over P naught, absorbance equals negative log of that. So really, for Beer's law to work well, you have to get good values for the measurements that tell you this. Okay. So one of the problems is if absorbance is too low. Okay. Say if absorbance is really low, what does that say about the transmittance? If absorbance is really low, transmittance is really high. Absorbance of the sample. So if the transmittance is really high, there's very little difference between the intensity of light between the blank and the sample. Then it maybe has a hard time telling the difference between those two. It's like two big numbers. You just got to tell the difference between the two. The relative error can be pretty large. So you don't want absorbance to be too low. Okay? But what happens at the other end? What happens if absorbance is too high? If the absorbance is really high, what does that say about transmittance? Really low. And then if the transmittance is really low through the sample, then hardly any light reaches the detector. Then again, it has a real hard time with doing that measurement because there's so little light intensity reaching the detector for it to measure. So Beer's law, the absorbance can't be too high or too low in practice for the instruments. But the equation itself is always true. It's just when you try to use instruments like we've shown you to make these measurements that there's limits. Okay, so absorbance of mixtures. Another thing we'll we'll mention. Absorbance is something that adds. So ideally, we would have a sample that has only one thing in it that absorbs radiation. So we take a spectrum, we go, oh, there's the absorbance spectrum of that one chemical that absorbs radiation. Like, say, yesterday, you were using this little part of the spectrum where really it was just caffeine that's doing the absorbance. Simple. But if you've got more than one thing in solution that's absorbing light, then the absorbances from the various things that are in solution, they add together. So that's the equation there, just to show that. This is that little piece from chapter 18. So this is like, say, Beer's law for component X, Beer's law for component Y, and for Z. And so this is the absorbance from that thing X. This is the absorbance from that thing Y, and then from Z. So drawn a graph here, absorbance as a function of wavelength. What's a good name for that graph? If I'm going to, something's going to be absorbance plotted as a function of wavelength. What's the name? Yes, absorbance spectrum. What if I had more than one of these? Say I wanted to show 2 or 3 or 4. What would I call them then? What if I had a bunch of these, multiple absorbance spectra? Yes. So spectra is plural of spectrum. I know most of y'all know that, but it doesn't hurt to reinforce that. So say you have this solution. Yeah, from yesterday's lab. Say if you tried to analyze Coca-Cola, yesterday's lab, all right? And we looked at the absorption spectrum between, what, 350 and 250? Okay, all right, well, does Coca-Cola have caffeine in it? Okay, so there's the absorbance spectrum from caffeine. But the problem with something like Coca-Cola, at least in the sense that it would be a problem for you, that analysis, is that it's dark and it's got a bunch of things in there that absorb light. And some of the things that are in there absorb light at the same wavelength range as caffeine. So that's why we had to analyze, in your procedure, kind of a clear or just like a slightly yellow kind of solution. But say if you did Coca-Cola, there was something else in there that absorbed light like that. So if you tried to record the absorbance spectrum of that sample with those two things in there, the machine couldn't tell them apart. The machine couldn't break them into the individual absorbances. The machine would just measure the overall absorbance. So what would the overall absorbance of this look like? I'm running out of colors. Well, it would just add. So here and here they would add. So the net would be like this. But here and here they would add big time. So this would be, so say if the green one is absorbance of, say, X. This other one is the absorbance spectrum of Y. Then the overall is the absorbance spectrum of X plus Y. So they add. All right. Let's do Beer's law, kind of a question. So mathematically, Beer's law is a great source of fun. There's about 100,000 different problems that you can do based on Beer's law. And this is just one of the things, one of the fun things that we can do. So let you have fun with this. All right. So before we show the excuse me, the answers that people have gotten, I want to invite someone to come up to the board to show their solution to this. I think what's going to happen is we're going to run out of time today. We're not going to be able to cover everything that's in those handouts, and we're going to have to draw the line in terms of what can be on the test fairly. So just things up to here, the Beer's law kind of calculations, and the basic theory of absorbance and transmittance that we've covered. I think it's worth the time to really go over the solution to this in a little bit of detail. I want somebody to come up to the board. Okay, we have a volunteer. Sorry. What happened here? Sorry, Fatima, can I ask you, what are the numbers that you've put down so far? What was the 69.7? Okay, 69.7 I think was a percent, yeah, okay. So they turn that into like just the non-percent ratio. Okay, okay. And you took the negative log of that. Okay. So that's your absorbance now. All right, do people agree with that or have any questions? Yay. Thanks for your help. Yep. There's a whole variety of questions that you can do. So here, you know, given percent transmittance, you can calculate molar absorptivity. But of course, you would need to have the concentration and a path length. But it's all kinds of questions. Let's see. What else is here? Yeah. That's where we're going to finish for today, okay?